What we're going to spend the last little bit of class doing is talking about sigma notation. Okay? Sigma notation. That's S-I-G-M-A notation. And that's what you see on this slide right here. Sigma notation is a way to represent the sum of a series. This is another way to represent the sum of a series. So instead of actually having the terms of a sequence listed out with addition symbols in between them, this notation can be used to indicate that you're finding the sum of a certain number of terms for either an arithmetic, geometric, or just any sequence in general. On the board, you see two examples of sigma notation. The Greek letter sigma is the E-looking symbol that you see here, the two symbols that you see. Whenever you see that sigma symbol, that means you are finding the sum. At the bottom of the sigma, there's always a variable equals a number. All right? And actually, this is a picture. I'm going to change this I to an N. That was my mistake there. That should have been an N. Okay? That variable at the denominator basically just tells you the variable that you're working with. You'll see the same variable in this expression that's right beside the sigma symbol. This represents the explicit form of your sequence, whether it's geometric, arithmetic, or just a random sequence with a rule. Okay? So the variable that's at the bottom of your sigma is going to be the same variable that you see in the explicit form. The number at the bottom that's equal to that variable tells you your starting term. So for this first example, that number is 4. That means you are starting with the fourth term of this particular sequence. So in the first example, I'm not starting with my first term and then adding however many terms. I'm starting with my fourth term. Okay? So the bottom number tells you what term you're starting with, and in this case, it will be your fourth term. The number at the top is the term you end with. So in this particular example, I'm starting with my fourth term, I'm ending with my 50th term, and so those are the terms that I'm essentially adding together from my fourth term to my 50th term. And these terms are what we get from the explicit form of the sequence. So how you use the sigma notation, well, actually, hold on, before we do that, let's take a look at the second example, okay? Again, as we can see, our variable is n, so that means that it's going to be the variable I'm dealing with in my explicit formula. In this particular problem, I'm starting with which term? What term am I starting with? One. I'm starting with that one, that first term. So for this sequence, when the numbers that I'm adding, I'm starting with my first term, and I'm adding all the way up to what term?
The eighth term.
The eighth term. Okay? So, one way to do this is to literally plug in 1, plug in 2, plug in 3, plug in 4, plug in 5, plug in 6, plug in 7, plug in 8 into your explicit form to get all of those terms and then add them up together. That is one way to do that. Literally plugging in 1 through 8 into that explicit form and adding them up together. That is like the default way to do this if you forget how to do what I'm about to tell you to do. That kind of sucks, especially for ones like the one that's on the left-hand side, because that means I'm going from the fourth term, the number 4, all the way up to 50, and that's a lot of terms that I got to sit there and add together. Your IB exams are timed, and that will take a lot of time, all right? But the other way that you could do this is by recognizing in those explicit forms are these arithmetic or geometric series that these sigma notations are representing. When you look at the one on the left-hand side, that -2 plus 3n, does that look arithmetic or geometric?
Arithmetic.
It's arithmetic. If you're ever unsure, you could start by plugging in 4, plugging in 5, plugging in 6, plugging in 7 to see if there's a common difference. So if I were to plug in 4, that'd be -2 plus 12, which would be 10. Okay, so if I plug in the 4, that's my fourth term. If I plug in 5, that's -2 plus 15. That would give me 13. That's my fifth term. If I plug in 6, that's -2 plus 18. That's 16. That's my sixth term. Okay? So, as you can see, the common difference is what?
3.
The common difference is 3. This is an arithmetic sequence. I'm going from my fourth term all the way up into my 50th term. And just out of curiosity, if I plugged in 50, that's -2 plus 150. -2 plus 150 is 148. That right there is my sequence. Well, kind of. I mean, I cut out the 7th term to the 49th term, but I have my quote-unquote 4th term, which is my first term in this case, all the way up to my last term, my 50th term. So if I can recognize that this is an arithmetic series, I can use the formulas for an arithmetic series to actually find the sum from my 4th term to my 50th term. We talked about this, I think, last week. Okay, I talked about this last week. I'm going to erase this so I can have some space. All right, remember there were 2 formulas for arithmetic series. There was this one, and then there was this one. If I can recognize this is an arithmetic sequence, I can determine what my quote-unquote first term is, which essentially is my 4th term because that's what I'm starting with. I can use these formulas to find the sum. The only thing I need to know is the number of terms. How many terms am I adding if I start with my 4th term and I go to my 50th term? How many terms is that if I start at my 4th term and I go all the way to my 50th term?
46. Right?
Careful. It's actually...
Oh, you have to count the...
Say it again.
You would have to actually count the 4th term and the 50th term, right?
Exactly.
Yes.
So it actually would be 40. 40 what?
If you had to count so it'd actually be 40.
Nope, not 48. It would be 47. So my number of terms here would be 47. So then I can use either of these two formulas to actually find my sum. Personally, I'm going to use this one right here. Why? Because I have my quote-unquote first term, which is my 4th term, and I have my last term, which is the 50th term. So then that'll be S sub 47 equals 47 over 2 times 10 plus 148. Then I just type that into my calculator and find my sum.
I got 3,713.
So 3713.
Yes, ma'am.
Confirmation from a different student?
That's what I got too. I got that too.
3713. So my sum for this particular problem, for this particular sequence, from my 4th term to my 50th term, is 3713. So sigma notation basically tells us what type of sequence we're dealing with, arithmetic or geometric, what term I'm starting with, what term I'm ending with, and by recognizing if it's arithmetic or geometric, I can use the actual sum formulas to actually find the sum. Instead of plugging in 4, 5, 6, 7, all the way up to 50 into the explicit form and adding all those terms up together. Let's do the one on the right. Okay, the one on the right. Is that arithmetic or geometric? Is that arithmetic or geometric? This explicit form.
Geometric.
It's geometric. So if it's geometric, well, we just went over geometric series today. Okay? That's the formula S sub n equals U1 R to the n minus 1 all over R minus 1. And since I'm starting at my first term, going all the way up to my 8th term, this one's a little bit easier because that's what we normally do, right? Starting from your first term all the way up to, a certain number. How many terms is that? Start with my first term, go all the way up to my 8th term.
9.
Careful.
8 terms.
It is 8 terms because technically you would start with your first, so that's 1, then 2, 3, 4, 5, 6, 7, 8. So this would be S sub 8 equals, I need my first term. Okay? If this is the explicit formula, I should already know my first term because it's U1 R to the n minus 1. What's my first term? 3. What's my ratio? 2. And I already know that n is 8. So then I just use the formula to plug in. Go ahead and plug in that into your calculator to get my sum. And while you're doing that, I'm going to show you the alternate way to do this that I strongly discourage, but it's like the last resort of what to do. Confirmation?
I got something different, but I might have done it wrong.
Okay. It should be...
I got 765 too.
Yeah, it should be 765. What you see in the thin black writing is me literally plugging in 1, 2, 3, 4, 5, 6, 7, 8 into the explicit form, and then you would technically add those together. I did that for the example on the right because, I only had to do 8 terms. I would never do that one for the one on the left-hand side because that's 47 terms I would have to write down and then add them up. It would take a long time, okay? So, again, sigma notation is a condensed way to show that you're adding a certain number of terms with an explicit formula, okay? So that's sigma notation. Let's take a look at this example right here. Is this arithmetic or geometric?
Arithmetic.
It's arithmetic. If you ever question it, you can start with the bottom number term and plug in until you start to see a pattern. So if I were to plug in 1, that would give me 2. If I plugged in 2, that would give me 5. If I plugged in 3, that would give me 8. If I plugged in 4, that would give me 11, and so on and so forth. If I plugged in 8, that would give me 23. This is my first term. This is my 8th term. Clearly, we can see our common differences. Common differences.
3.
And it's the same number that's attached to your variable in an explicit form. Okay? Just like how I said last week with arithmetic sequences, the number that's beside the variable is your common difference. So since this is arithmetic, I can use my arithmetic formulas. What is going to be the value of n? How many terms am I adding? How many terms am I adding?
8.
8. All right, and since I do know my first term and my last term, I'm going to use the shorter formula, so that's going to be 8 over 2, 2 plus 23. Then I'm able to find my sum. That's going to be 4 times 25, which is 100. And that's the sum of the first 8 terms of this arithmetic sequence that follows the rule 3i minus 1. Try this one on your own. So we have arithmetic or geometric?
Geometric.
This one's definitely geometric. I mean, it's set up in that way. This is u1, r to the n minus 1. So it's definitely geometric. So that means I'm adding a certain number of terms. My first term is 1/2. My common ratio is 2/3. The only thing I'm missing is my number of terms. What's my number of terms that I'm adding?
14.
14. So that means I'm going to need to raise 2/3 to the 14th power. Okay? So when I do that in my calculator, which I'm going to have to share that screen so you guys can see it. Okay? I'm going to do, well, let me do it in like the not so fancy fraction way. I need to raise 2/3 to the 14th power. So I put that in parentheses, and I'm going to put a 14 there. By raising 2/3 to the 14th power, that entire fraction, I'm going to get a decimal. I need to subtract 1 from it. I'm doing my entire numerator right now. Then I need to multiply this by 1/2. This is my entire numerator. Then I'm going to divide it by my entire denominator. My denominator was 2/3 minus 1. 2/3 minus 1 is a negative 1/3. So I'm going to divide by a negative 1/3. I put that in parentheses so the calculator knows I want the entire numerator divided by that entire fraction. So then when I click enter, I should get 1.49. Not multiple nines, but just 1.49. And that is my sum. Unfortunately, we can't convert that back to a fraction, so we'll have to leave it as the rounded 3 significant figure number. Because it doesn't have a pattern either, so that means it doesn't, it's not going to end. And it's not a repeating decimal.